We're going to solve this variable coefficient second order dE, which is a version of what's called an Airy equation. We're going to solve this initial value problem using a power series solution. Now, I will warn you ahead of time that power series solutions are pretty technical to work with, and there's a lot of mechanical details you got to go through. Now, this polynomial equation has no y prime term. So if you take a look at it here, p of t would be 0, and q of t is just this linear function 1 plus t. So they are both analytic. And that means every single point that you want is an ordinary point. What that means is that you can pick any point you'd like to be the center of your power series. So we are going to let y of t be a power series that looks kind of like this, n equals 0 to infinity, an, and we're just going to pick tn. So t naught will be 0 as our center. So this is going to effectively be an approximate solution. It's kind of like an analytic approximation to the solution. The more terms we get, the better the approximation is going to be. And they're going to be centered at 0. So you're going to see that once I show you the picture of the solutions, they'll be most accurate near 0, and you'll need more and more terms to gain accuracy as you move away from 0. So the idea here is that we're going to have to sub this into the dE. And to sub this into the dE, we need to differentiate. So we'll need the t derivative of this solution. Now, as I mentioned, we are going to assume that we have all the convergence we need, and that means that we can apply term-wise integration or term-wise differentiation. So what that means is effectively we can pull the derivative inside. We'll get an n equals 0, a to the n, derivative of the power term, which is going to end up giving us n equals 0, an times n times t to the n minus 1. Now here's some quirk that happens with power series. Because n is starting with 0, the first term in this series is going to be 0. So rather than carrying around this redundancy, what we're going to do is change the starting value of the index to be from 1. So we'll have n, an, t to the n minus 1. Now, similarly, if we were to take the derivative again, what we would find would be n equals 1. We'll have n minus 1, an, t to the n minus 2. Now, once again, because n equals 1, the first term here will be 0. So what we're going to do is rewrite that starting index and start it at 2. And we'll have this expression for the dE. That means we've got to plug all of this stuff back into the dE. So the dE is y double prime subtract 1 plus ty is 0. So we're going to have this expression for the second derivative. We'll have n equals 2 to infinity, n minus 1, an, t to the n minus 2, subtract 1 plus t into this power series, starting n equals 0 to infinity here. Now, keep in mind that the goal here is to find all of these an's, infinitely many of them, that are going to make the left-hand side of this dE equal to the right-hand side. That's the goal. That's what we're ultimately trying to look for. So we've got a lot of algebra to work through. We'll have n equals 2, n minus 1, an, t to the n minus 2. I'm going to distribute this term here, so I'll have subtract n equals 0 to infinity, an, t to the n, plus t, n equals 0 to infinity, an, t to the n. I'm going to take this power of t because it doesn't have an end. I'm going to pull it into there. And so what's going to happen is I'll have n equals 2, n minus 1 an t to the n minus 2, subtract this other expression, an t to the n, plus another summation where I've got an t to the n plus 1. And all of this is going to be equal to 0. Now there's the next quirk that happens when you deal with power series methods is that if you take a look at the index and the power, you're going to find that they all generally start at different powers. This thing is going to start at the power of t equals 0. This is going to start at a power of t equals 0, but this is going to start at the power of t equals 1. So now, what we need to do is we need to ensure all the series start at the same power of t. Why? Because we're going to try to combine them into a single series. And if that's the case, what we have to do is effectively what I'll call let out the first term of these t equals 0 to have the powers match. So that means, yes, you've got an infinite series. If I take the term in that first series where n is equal to 2, I'll have 2 times 1 times a2 t to the power of 0, n equals 3 to infinity, n minus 1 an t to the n minus 2. Here, I'll have an a0 minus the summation n equals 1 to infinity, an t to the n, plus this other summation, which already starts on the power of t to the 1. So this is good. Now I've got two terms that are constants, plus I've got all these other series. They all start with a t to the 1. But there's another issue. There's always an issue. They have different starting values for their index. That's no good. This index starts at 3, this one starts at 1, this one starts at 0. What we have to do is we're going to have to redefine the index so that we can combine them into a single sum. So that's a bit of an annoyance that you have to deal with when it comes time to dealing with power series solutions, but it's just a matter of making a substitution. So in this first summation, what you're going to do is look to the exponent to give you a little clue. In this one, we're going to let j equal that value of the exponent, n minus 2. So that means if you needed to, you could replace n with j plus 2, which we're going to need to in these coefficients. Now, when n is equal to 3, this is going to tell you that j starts at 1, and clearly when n goes to infinity, the other one will go to infinity as well. So we'll have 2a2 plus a summation here where j is equal to 1 up to infinity. We'll have j plus 2, j minus, or j plus 1, because that first expression is an n minus 1, so that's going to go away. And now the index here will be a subscript j plus 2, and this will be t to the power of j. So now that first summation starts with a power of 1. We'll have an a naught that came there from before. Now, we want this next summation here to start at the same power. And so in this particular case, there's not much we need to do. Here we'll leave it so that j is equal to n, and we'll start everything at 1. And in this last case here, what we're going to do is we're going to let j equal to n plus 1, so that when n is equal to 0, this means j is equal to 1. all of these things are going to get us exactly the expressions we need. And this is going to give us the nice result that all of our indices start at the same value. Sometimes I just swapped the letter, and in other cases, I didn't. So up here above, I'm sorry, I forgot a negative sign all the way over here. So this should be a negative, and this should be a negative. So scrolling down, this term here needs to be a negative. And that means that here in this summation, I'll have j equals 1 to infinity, a to the j minus 1, t to the power of j. All of this equals 0. So it's pretty tedious. But all of that work needed to get done so that we could finally combine things into one series. And so we've done all the work. We've got j plus 2, j plus 1, a subscript j plus 2, subtract aj, subtract aj minus 1. All of this is now the coefficient of this term with j, x to the j, t to the j, sorry. The left-hand side will equal the right-hand side. Remember, the right-hand side is 0 only if every coefficient for every power of t on the left and right is the same. Well, take a look at the right. All we've got are zeros, so every coefficient for every power of t is a 0. What this is going to do is lead us to an infinite system of equations for each ai. Now that may sound horrible, but that's not bad at all. So for example, for the t to the 0 term, the constants, we've got 2a2 minus a0 is 0. That's going to give us a relationship that a2 is a half of a0. And now for all of the other ones, we're going to take that expression that was in there, j plus 2, j plus 1, a minus all of this stuff, and this has to be 0. So what we do is we reorganize this for the highest index there, and we'll get aj plus aj minus 1 over j plus 2, j plus 1. And this is going to be valid for j being greater than or equal to 1. This is called a recurrence relationship because you need previous values in order to be able to calculate the next value. And what you'll notice is if that j starts at 1, so for example, if j is 1, you'll have a3 is going to be related to a1 plus a0 over 3 times 2. We don't know what a0 is, and we don't know what a1 is. And so this is the point in the story where what's going to happen is that we will get an interesting idea. And sorry, I'm just going to delete this picture and put it down here. And that'll be what's coming up next. So I've kind of ruined it a little bit, but oh well. Now, remember, we are supposed to get two linearly independent solutions. And they have to be series form. Well, to get the two linearly independent solutions, it's all going to come back to choosing values here. We're going to let, in the first case, a0 be arbitrary, and we're going to set a1 equal to 0. Now, in the second case, we're going to let a0 equal to 0, and we're going to let a1 be arbitrary. And when we do this, we're going to get a bunch of terms. So, A naught is arbitrary. So that could be anything. A1 is 0. A2 is a half of A naught over 2. So half of A naught. Now, here's where the recurrence relationship kicks in. We're going to have, when j is equal to 1, we're going to have A1 plus A naught over 3 times 2. The A1 is 0, so this is just going to be A naught over 6. A4 is going to be A2 plus A1. Well, that's 0. And this is for j is equal to 2. So that's going to be 4 times 3. But A2 was A naught over 2. And then that's going to give us another 3 times 4 on the bottom. So this is going to be A naught over 24. And I can just keep proceeding this way. A5 is going to be A3 plus A2 over 5 times 4. Well, A3, we had an expression for, was A naught over 6. A2 was A naught over 2. And then we'll have 5 times 4 on the bottom. Well, as you keep going through, you can see that this is starting to get kind of messy. And what's going to happen is that you can just keep repeating this. Now, on the other side, if you set A naught equal to 0, A1 equal to 1, or arbitrary, so we'll just call it A1. A2 is also going to be equal to 0. A3 is now going to be, as before, A1 plus A naught over 3 times 2. So that's going to be A1 over 6. A4, so this was when the recurrence relationship had j is 1, j is 2. This is going to be A2 plus A1 over 4 times 3. Well, A2 is 0. This is going to be A1 over 12. And j equals 3. It's going to be A5. And you see that this just becomes a lot of grunt work, right? Very tedious, lots of work. A1 over 6 times 5 times 4, so on and so forth. In this way, we create two linearly independent solutions. And I'll show you what they are here. One of the solutions, y1 of t, is just going to come from all the terms with a naught. So everything's going to be some multiple of a naught. It's going to be a naught t to the power of 0 plus 0 t to the power of 1. And then the a2 was a half t squared. The a3 was 1/6 t cubed. 1 over 24 t to the 4. And then as we keep going, we're going to get different size terms. We'll get 1 over 30 t to the 5, 1 over 144 t to the 6, so on and so forth. This is where a program like Maple is able to easily calculate all of these recurrence relationships for you. Now that's just one of the solutions. The other solution, let's say A1, this is going to give me another term. We'll have a 0 plus 1 t to the 1. Now the next term there is going to be a 0 t squared. And then as we kept going, we'll have 1/6 t cubed. And then we'll get 1/12 t to the 4, and so on and so forth. Plus 1 over 20 t to the 5, so on and so forth. So it's awful, but that's an explicit form. It's not closed because these series go on forever. The general solution is going to be a linear combination of these two. Unfortunately, there's not going to be a general way to combine all of these things to make them look nicer. You can apply the initial conditions. We had y of 0 is equal to 1. And so that means all the terms in the y2, all y2, this is just going to give me 0. Everything in the y1 term is going to go away except for a0, so this is going to tell me a0 is equal to 1. If I differentiate everything here, what I'm going to find is that all the terms in y1 go away when I plug in 0. So if you take a look at y1, there's a constant term and then no linear term. So the next term will be a t. So if I plug in 0 into that, that's all going to go away. The only term that's going to be left is this one. So if my initial condition is 0 here, this is going to imply that a1 is equal to 0. So the unique solution to this initial value problem is just 1 times this series. I'll have 1 plus a half t squared plus 1/6 t cubed plus 1 over 24 t to the 4 plus 1 over 30 t to the 5, 1 over 4, 144 t to the 6. Just goes forever and ever and ever. What do I do with this? Well, as I said earlier on, this is an approximation to the actual solution. It's an approximation because if n is not infinity, it's an approximation. It's only exact as you take the limit, n goes to infinity. But that doesn't mean we can't do anything useful with this. So if you take a look at this picture here, the curve in black is the exact solution. And this is obtained just by taking lots and lots and lots and lots and lots of terms. All these other lines are for different values of terms, different number of terms. So this is going to be 5 terms. And you can see that it only matches in this small area. But if I were to take 10 terms in the series solution, that interval gets a little wider. This one here is with 15 terms, and you can see that it's starting to match very, very well. You can't notice it, but because it's exactly matching there. As I keep going further, this is 20 terms, and this is 25 terms, and this is 30 terms. It gets better and better and better. So what you'll see is that, remember that our center was at 0, and as we increase the number of terms past 0, the overlap with this black curve gets better and better and better and better. So it isn't perfect, it isn't nice to look at, but these series methods actually give us a function to work with. All of those equations I gave you at the start of the videos with the fancy names on them, they've all been solved using series solutions. People have spent their entire careers coming up with properties of those solutions and giving them nice little symbols instead of working with the horrible series. So you can do a lot of good with them. But they're all based on this basic idea.